Go.
Okay, so this is gonna be the third physics lesson, and hopefully we get through it today because we are on a tight schedule and the schedule's been falling apart. That's mainly because like physics is meant to be like really detailed because it's like for most people it's a little bit difficult to comprehend. So we just need to like bulldoze through this lesson. But anyway, so I'm gonna restart this drafting thing like as a quick review, real quick. But so it's actually like really laggy if I write on this whiteboard. So I'm gonna switch tabs uh to draw like a rough estimate of what's happening. Okay, so displacement time graph, right? And we want to graph the velocity. So last we determined that we justify that this is in uniform motion. A displacement time graph that is made out of diagonal lines, all right, represents uniform motion. That means that the speed in given time intervals does not change, okay? And the reason why we can tell that the speed does not change is because the slope of the lines in the displacement time graphs, the DT graphs, the slope is constant at each point. So, like at this line, right? This line will have a slope of whatever, of some value, and it's going to be the same here, 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 and here, and here. But if we had something like a curve, right? If we had something like, oh my God, this is so difficult to write. Okay. If we had something like a curve like this, the slope at each point is different. Like here, we can tell it's flat, but here it's steeper. So that means that the speed would be changing. So that's why uh, we have straight lines here. So that's why we can tell that it's in uniform motion. So let me just write it here. Uniform motion equals speed does not change. Does not change, like triangle. This is pretty bad symbols, but you know what I mean. So the speed doesn't change at any given point in the specific time intervals. Okay, so if we remember the formula so the way you convert from a dt graph to a vt time graph is a slope, and the slope's formula is m equals y2 minus y1 over x2 minus x1. And these are corresponding points. So this is a point that we use, and this is a point. I don't like this color. And this is a point that we use. Sorry, not the minus sign. Okay, that was horrible, but you get the point. So either way, that is the conversion factor that we are using from dt to bt, and then we're gonna learn how to change it to at as well. And there's ways you go from back to forth. Okay, so this we know that it's a slope, and so I don't think last time I explained why it was a slope, so I'll do it this time. So the reason why it's a slope is because we can look at the unit analysis of the slope. So um, for a dt graph, right, your time is in seconds, your speed is in meters. So the slope, and this is your y's, these are your x's. So the slope would have meters in the top and seconds in the bottom. So this would tell you that the slope would be your velocity because of units, and it just made sense. Think how rate of change is similar to the change of distance per every time. Like it's all interconnected, so don't worry about it. Okay, so now let's actually try and find some information here. So from 0 to 4 seconds, right? Uh, in the span of these 4 seconds, the person travels 4 meters, right? So you use the formula v equals d over t, or you can use the slope. It doesn't matter. But uh, for for the sake of time, we're going to use d over t. Oh wow, that was embarrassing. Okay, hold on. So sorry, v equals d over t, and remember this formula only works for uniform motion only. Okay, so v equals d over t. travels 4 meters and it's 4 meters up, so positive, right? We're just gonna remember that as positive. So we're gonna say north, positive, south, negative. Okay, so 4 meters in the span of 4 seconds. So the slope would be 1 meter per second. I mean, the speed would be 1 meters per second, positive, so it would be north. All right, so the way we represent it on the VT time graph is that we would essentially, so these are different segments, 1, 2, 3, 4, right? So from 1 to 4, it would be a vertical, horizontal line of 1 because the speed throughout, remember, speed does not change. So the speed, I mean, the velocity throughout that time would be the exact same. So it would like, they would connect to here. Okay. Stop me if you have any questions because I think I'm going a little bit too fast for your liking. But yeah, just feel free to ask questions if you're confused. And we'll like after I'm done the drafting part, I'll ask you if you have any questions. Then we'll do like an example. All right. So then the next part is pretty straightforward. And then here, the distance does not move. It stays at 4 the entire time. Right? If it doesn't move, we already know that it's going to be a 0 because there's no distance. 0 distance over 4 seconds will be 0 speed. So it will look like that. So it will be here. No speed. Speed is 0. Velocity is 0. Okay. So in these 4 seconds, we can see that the person travels from where she was at 4 meters north away. Uh, the object travels 4 meters south back to the original place, right? So we can use this formula to describe that again. So 4 meters minus 4 over 4 seconds, negative 1 meters per second, which is 1 meter per second south. So how do we represent this? Well, 1 meters north is a horizontal line at 1. So for south, it'll be a horizontal line at -1. Okay, so that would be represented here. Oh, this side's very laggy, so if I like miss something, just imagine that I have a perfect computer and I put it there. Okay, so from 12 to 16, we can see that this person goes. We can see that this person moves from his original place 2 meters north. 2 meters north. I mean 2 meters south because it's in the negative quadrant area. So same formula. All right. Okay, so let's do this one with slope actually. So slope we need 2 points. So I highlighted these 2 points. So this point, all right, is 12. Oh my God, 12, 0. This point is 16, 2. And remember, the units are in meters and seconds. So write that. Yeah, Rachel, is this really laggy? Because hello, does it look like it's pretty laggy, right?
It's kind of laggy.
Okay. So let's do that question with slope. So slope y2 minus y1, x2 minus x1. Okay, so
it's working all right now.
coffee. Yeah, because I'm on the board where there's not that much writing, so like it's like it's not as crowded and clogged up, so it's faster. Okay, so with coffee bears Angela, right?
Right?
Right. All right. So Angela, so if we have this formula and we have these 2 points, what would I substitute into here? What would I substitute in the slope formula with these 2 points? Just open your mic and just talk.
I'm sorry, I was taking notes, so like I kind of missed that part.
All right. Let me just go over this then. So, this is a pair of points. Remember slope. This is a pair of points. So we just need to put them in. So let's say this is the y2 point and this is the y1 point. All right, so the y2. So I mean, this is like the 0.2. This is 0.1. Oh my god, this is so laggy. Okay, so this is 2. Then y2 would be 12. Oh, and then y and the x1 would be 0. I mean, x2 would be 0. Okay, and then we subtract the other set of points. So the y in this set of points is 16. The x in this point. Okay. Oh wow. I think I switched it. Yeah, I switched it. Wait, did I switch it? Wait, two. Okay, this is just really sad. This is just embarrassing. Okay, hold on. It is 12. The points are 12, 0, and 16, 2, but these are the x's and these are the y's. So y2, x2, y2, x1, y1. All right. Let's just whatever I just said. Like when you go over the recording, just replace all the 12s and 16s with y's instead of x. But yeah, so I'll just redo it again. So 0 and then 12 here. The set of points is the y is the 2. These set of points are the 1. So 16 x in the bottom, y on top. Okay. So now we just do some simple math. 0 subtracted 2 is -2. 12 subtracted 16 is -4. It simplifies to 1/2 meters per second. Remember, these are units. Put units in because we're taking measurements, they're not numbers. Half a meter per second, and it's north. Is it north? I don't think it's north. I think I'm tripping today. Hold on. There's something not right about this. Yeah, this is -2. Okay. Wow. Okay, I'm making a lot of mistakes. Sorry. So this is -2. So we add 2. So this will be +2. This will be -1/2. So it will be half a meter per second south. So how do we represent this chain? Wait. Something is wrong. Okay, wait, Rachel, can you double check my work? I think I'm like tripping right now. Yeah, hello.
Private chat.
Wait, can you double check what I'm doing?
Check chat. Private chat.
Okay, really interesting. But basically, even though I drew it as a constant line,
Mhm.
I'm pretty sure that the slope here is different from the slope here. Because this slope here is 1, but this slope here is half.
Oh yeah. See if I can.
Okay, no, I think I got this. It's fine. All right, so if it's half, like we already know how to represent it, halfway between 1 and 0, so around the graph, it will be like here. All right, and you're probably asking like why they're just random lines, like why are they connected? Well, this is an unrealistic situation, obviously. Like you can't change your speed that quickly. It's not instantaneous in life. Like you always have to decelerate and slow down. So these are unrealistic portrayals, but these are just like simple methods of graphing. So yeah, so that's why the speed changes so drastically. It's unrealistic, but it is just how to represent it through graphs. All right, now let's go over this. So 2. So the person was originally 2 meters south. He goes back to his original place, so that means he moved 2 meters north. So that's positive 2 meters. Where are these calculations? So he was 2 meters north in the span of 4 seconds. So half a meter squared north because it is positive. So that means half a meter squared north. The last interval will be halfway between 1 and 0 at 1/2. So it would be here. So that was the process on how to convert from a displacement time graph to a velocity time graph. And on a test, I don't think in grade 10 you really do that on tests, but like in 20, like in tests, you have to show like the full conversion. So like a slope calculation basically for every section. So it does get a little bit annoying, frustrating, but it does happen. All right, so trick question now. What is the definition of acceleration? Hello? Hello?
Okay, so basically, acceleration is like how like it's like the speed that like how fast like
All right. So basically, acceleration describes the change of velocity. So it describes per how many speeds does it increase or decrease per every second. Remember, those are our units for acceleration. Meters per second squared, because it represents the speed change per second. So, yeah. So with that in mind, right? And what is the definition of uniform motion again?
uniform motion is like the speed that is staying constant.
And does the speed change at all if it's constant?
No.
It doesn't. So does the object accelerate?
No.
No. So the speed does not change, and there's no acceleration. What would the value of your acceleration be?
0.
Yeah, 0. Good job. So that means that this acceleration time graph, this is 0. Throughout the 20 seconds, there's no acceleration. So we just put a straight line on 0. Okay?
Yeah.
All right, so let's move on to this question. All right, this question a little trickier because now we have to convert from velocity to displacement to acceleration. Okay, so we just went over that the slope of the displacement represents the velocity. Oh, also, the way you convert from velocity to acceleration time graph is also the slope. So why do you think the slope of the velocity represents the acceleration time graph? So remember that we looked at the units here, right? It was per meters per second for distance over time. So velocity over time would be meters per second over second, which is also meters per second squared, right? Does that make sense? Okay, and also you can think about it as this. The definition of acceleration is the change in speed, right? And then the slope represents the change of y proportional to x, which means that in the terms of velocity, the change would be acceleration. So it would be slope, okay?
Okay.
All right. And then the slope of a vertical, like a horizontal line, is always 0. You can note that somewhere. So m of horizontal is 0. And we can prove that because if it's horizontal, the y's don't change. So y2 would equal y1, which would be 0. So it would cancel out. But I think I'm diving too deep into a simple concept like slope. So we're going to take it back to the notch. All right. So I'm going to redraw that graph actually. So do you have any ideas on what things might convert velocity back into displacement? Hello?
Yeah.
Yeah, so my question was, do you have any ideas on how we could convert velocity back into displacement?
Mm,
So I'm not expecting, this is like I haven't even taught the curriculum yet, but what you're going to do is you're going to use, and also these should have vectors on them. Didn't the habit of doing it. I'm not doing it because it's just an extra step, and I always remember to do it on tests, so it's chilling. So the conversion that we are going to use. Also, I should note that this is like the gold star of graphing. Okay. Also, so from velocity to displacement, it is area. Okay, you find the area between where your point is and the x-axis. So an example would be from 0 to 2, we want the area of this. All right, and then we want the area of this. We want the area of this, and we want the area of this. So, the area we want under the specific times tell us the displacement after those times have passed. So the area of the red, the area of the red is a displacement at 2 seconds. Okay, so this is really important to note because you need to find a lot of points to draw like a general shape of this graph, right? You can't go about just like finding like 8. Like let's say, oh, 8, I'll just find the area of this, and then I'll have my entire graph. I'll just like draw a line. No, you can't do that. You have to do a few points to get a rough shape of what the graph looks like. So this is why we have to find the area of all these little parts so we can piece it together, okay?
all right.
So it's something to note, which could be important, like I might ask a question about this on tests, and they probably will, is that the final displacement, all right, is the top area, so top area minus the bottom area. Okay, so the final displacement. So like I said, right, this is why we have to find individual points. If we find the top area and the bottom area, and we did an area, and let's say it's like here or something, right? We can't just draw a line here and say, oh, this is displacement time graph. That's not how it works. We have to go through the individual moments in time to find out what the person's speed was, to find out how far the person moved to draw the graph. Okay?
All right.
So why is it top area minus bottom area? Well, if you remember, displacement is a vector, right? Like you add up all your little like distances, right?
Mm-hmm.
So if you add up the positive distance and the negative distance, you're basically subtracting the positive by like these two are the same thing. Okay, so if these two are the same thing, that means that I'm explaining this poorly, but what I'm trying to say is that uh, this is a negative. Like this is a negative. This green and blue uses negative velocity, so it would get a negative displacement. So if we add them, we could get the same answer. Or if we use positive velocity, like we just use the magnitude of the number and subtract it, we'll get the same answer. But it's because of a plus and minus thing. Like I don't know if you understand what I'm saying. I don't know if you understand what I'm saying, but basically, it's an addition of vectors, and one of them is a subtracting sign, so it's like subtracting. That kind of is a trash. It's an okay explanation, I would say, but we'll see. But just remember, this is the formula, okay? Hello?
Yeah.
Yeah, like when I say like okay, just like try to respond. so
Alright.
I can see where your path is. Okay, so this is pretty straightforward now. Area. So what would the area of the triangle be? And I'm pretty sure I put this at 10. Yeah, 10. What would the area under what would the red portion be? What would the area of the red portion be? Do you know the area of a triangle?
Yeah.
Okay, so b squared over 2. So what would the area be?
Hold up.
The base is 2 seconds. The height is 10 meters per second. Divided by 2, the area would be, so you see how the units cancel out? The area would be 10 meters, quote unquote area. So that means that in the displacement, it goes to 10. Okay?
Alright.
That's what we're marking. But so what if I ask you like a math question? Like you just enter in your calculator and then you should be done. You don't need to do anything extra or whatever you're doing that's taking so long. So yeah, so just relax because we're just doing calculations. Okay, so how do you think we draw the line here? How do you think we draw the line? Like what do you think the shape of the line is if we drew it? So remember, in here, the shape of the distance time graph were vertical lines, were straight lines. So what do you think would be the shape of the line from here to here?
It's okay to say I don't know.
Yeah.
I don't know.
Okay, so it wouldn't be a straight line because the speed is clearly changing, right? Can you tell the speed is changing?
Yeah.
Okay, and changing because it's not a straight line, right? Okay, so we would have to represent if the speed was changing in a situation, we would have to draw curves. So this curve will roughly be flat. So I represent flat by 0, and then it goes up and it curves to positive. Okay, because this means, because in here, if we look at it, right, the speed starts from 0 and it gets faster because it's going 10. Okay, it's went from 0 to 10. It's going faster. So if it's going faster, right, that means you can travel more distance per time if something is going faster. And if something's going slower, you travel less distance per time. So a good way to think about this is if you run. Like this represents someone running. All right, they can go this much and this much and this much and this much. So you cover more distance per time if something's getting faster. And you know if something's going faster if it moves away from the y, away from 0, away from the x-axis. So away from x-axis, or 0 equals faster. And if it's going to the x-axis, it is going slower. Okay?
Alright.
All right. And now I just want to bring up a quick, so I wrote it here, characteristics of slope. Oh my God, what am I doing? So let's analyze, so let's analyze some things from the slope. So the only curves you'll see are on displacement time graphs. So 1, 2, 3, okay. 4, there's 4 characteristics. So this is a common, these are the common curves that you're going to see. All right. So let me just go over them. This is mostly memorization, but if you're good at like using reason and logic, you shouldn't have to memorize them. So note that slope equals the velocity. Okay?
All right.
All right. So in this slope, in this line, right, is the line getting steeper or flatter?
Flatter?
It wouldn't be getting flatter because it's literally like going really, really high up. Like it's by flatter, I mean like flat. Like this is
Sorry, I
what
thought you were.
flat looks like. Huh? Like what? I didn't hear you there. Wait, what did you say? Hello? Are you still with us? Okay, anyway, so it gets steeper, right? So because it gets steeper, right? This tells us that the speed is going faster or slower.
Uh, faster.
Yeah, it's going faster because if the slope is bigger, if the slope is getting bigger, the speed is getting bigger because speed is equal to the slope, and steep equal a greater slope. So a greater slope would equal a greater, and flat is the speed is getting lower, so the speed also gets lower. All right, so a graph that looks a line that looks like this on a DT graph. Oh wait a minute, what just happened? Sorry. There's a lot of this is really weird. I couldn't draw for some reason. Okay, I don't know what's happening right now. I cannot tell you what's happening. So I'm just making a new whiteboard then. But why is it so slow? I'm gonna stop the stream here because I need to figure this out. Why? What? This is an issue.
We can start break now, since if you look in your upper left corner of the screen.
Yeah, I don't have that anymore. I joined Zoom from browser, so I can't see these type of things.
We can start the 10-minute.
Oh, okay. A whiteboard started. Wait, how many more minutes are there?
Huh?
How many more minutes in the meeting? All right. So I guess we can quickly go over them. Sorry, these are really messy. If I had a real whiteboard, I would not do this. All right, so now you know what a steep slope represents on a DT graph. So this would mean that if it's faster, it's moving away from the x-axis. It's moving away. It'll be moving away in this direction, and the slope is positive because I don't know if you learned this yet, but the positive slope looks like this, and the negative slope looks like this. So you know what the slope is, so therefore you know what the speed is, so you know which quadrant it's in, we know which half it's in, so we're good. Okay, so now let's look at this now. So this is getting from steep to flat. So what's steep to flat? So if something's getting flatter, it's getting slower, okay? So if something's getting slower, it moves away, it moves to 0, remember? So it moves to 0, then that means the ending point should be here. So where would the starting point be then? Well, the starting point would be here. The distance, right? Okay, so the speed at start when it starts, the speed is going hella fast because this is really steep, right? So this is steep, big speed. I mean big speed. This is flat, so it's little speed. So that means the line will look like this. It goes from really fast positive slope. So positive slope means speed. So positive speed to 0 because it goes to 0 because it's flattened out. So remember, you also need to remember that a flat line equals a slope of 0. Yeah, so I think right now I'm throwing a lot of information at you because it's all connected in one. Like these pilot prep lessons are like cram lessons, so you can ask me questions or rewatch a recording. But I feel like if I keep talking about like a slope of something, it will be really repetitive. So I'm gonna try and stop going on tangents, but we'll see about that. Okay.
Meeting's gonna auto end.
Okay. Have a good break then. And based on these two shapes, try and draw the velocity time graph. Knowing what you know about slope and what a flat slope is, what a steep slope is, and the relationship.
Come back 420.
Yeah. All right. So if we're gonna do a quick review of what I just wrote, like if I were to put it all in one word, it would be, oh wow, that was a horrible writing. Okay. What? Okay, yeah. So it would be, so if we're on like DT graphs, right? The steeper the slope is, all right, it means a faster speed. It means, and these are for curves, by the way. So I'm gonna write curves. So a steeper slope would mean a greater speed. Velocity, which would mean away from 0. And note that this is a line. And you need to watch out for positive or negative. Okay? And then if there is a flat slope, right, it means it is a lesser, like it gets, the speed gets less and less. So it goes to 0. And it is a line, positive or negative. And remember that a slope of a flat line is 0. This is essentially a summary of everything we just were talking about. Like it's a relationship that pieces it together. Okay? Tell me if you need more time, Reagan.
I know I got this one now.
Okay. So let's go over here and let's check these out. So based on the rules that I just said, right? Here, I'll deduce this one for you and you try the next one. Okay. So for this one, it gets steeper. So it's steep. So you know it's steep. You know it's negative. This means it moves away. And it is a line. So it would move like this. Okay. So then, and it's in the negative direction. So that means it moves with negative speed. So the speeds would be more and more negative because there's more and more speed. So yeah. So negative doesn't mean getting smaller. Negative just means different direction. So could you explain to me what a curve that looks like this would look like on a VT graph?
Okay, so first,
First, we determine the sign, remember? So
Yeah.
sine, and then how steep and flat it is, and yeah, so. All right, what's the sign? All right, just explain it in your own words. I won't guide you, but try to explain it. Okay, start.
okay, so I think it's a flat slope.
Yeah, it gets flat. Yeah, okay. So, all right, so the first step was a sign. So what sign is it? What direction is it?
Oh, is negative.
Okay, yeah. Okay, next. What do you figure out next?
So So it should be like going to the
No. Explain the process. Okay, so we know it's negative, and then we know it's flat. So what does this tell us about the speed? Is it getting faster or slower?
It's getting slower.
Yes, because a flat slope means slope of 0, which means speed is 0, which means not moving, which means slow. Okay, so it's getting slower. So what does a slow speed, how do we represent a speed that's getting slower? How do we represent it?
We start off from like I'm sorry, what is that thing you just wrote?
What thing?
The one was like, so the one below the V.
Slow,
Oh,
getting slower.
okay.
So if it's getting slower, something moves to 0 or to the x-axis. So this is a concept you need to understand, that slower means not moving. So that means it goes to 0 if it's not moving. And 0 is the value of the x-axis. So how would it look like if it's going to the x-axis?
It will start from like it'll start from where like
All right, so let's say here and here. This is point A, this is point B. Where did it start?
we start on point B.
Right. So why does it start on point B?
Because it's negative.
Okay. And then where does it go to?
It goes to the 0. So
What is the 0 called? What is it called?
The x-axis.
Yeah, x-axis. Okay. So to summarize, I'll summarize one more time. This creates this. This creates this. This creates this. This creates this. D V. Okay?
All right.
Tell me if you wrote that down.
Yeah.
All right. So, based on the information you just learned, right? So we're gonna draw rough diagrams of graphs. So you're gonna convert a dt to a vt, but it's gonna be like a rough conversion. Okay.
All right.
All right. But while we're on the topic of these type of slopes, right? All right. Let's convert some vt type slopes now. So we can convert these slopes into at slopes, acceleration. So all of these slopes, all of these graphs accelerate. And why do they accelerate? Hello? Why do all of these scenarios have an accelerating object?
Because it is like it is an object moving.
Okay, well, something can move and doesn't have to accelerate. So in these scenarios, why is the object accelerating? Okay. It's okay if you say I don't know, but just say I don't know. Do you not know? All right. Okay, so way back we defined acceleration as a change of speed. So change of speed means acceleration, and here all the speed changes, and you can tell that the speed changes because it's not the same. Like here there's 0, here it's a number, here it's less, here it's more. It changes, so there's an acceleration for all of them. Does that make sense?
Okay.
All right. So let's see if we really understand this concept. Okay. So what was the conversion factor from how do we convert a velocity time graph to an acceleration time graph? What device do we use?
Sorry, from what to what?
From velocity to acceleration.
From velocity to acceleration.
It was in one of our little tables. Yeah, it was here. This is the most important part of this entire drafting section. So it's slope. The slope of a VT draft determines the acceleration time draft. Does that make sense?
Yeah.
And I already went over it like 3 times on why it is, so we won't be meddling that. So this line here, does it have a positive slope or a negative slope?
It is a positive slope.
Okay, so and the acceleration is constant, like this a linear, okay? Lines have constant slope. This is also a concept that helps determine our drafts. So since lines have a constant slope, what would the AT time graph look like for this if the slope is constant?
It would be like straight line.
It would be a straight line that is vertical or horizontal. Like, is it slanted? Is it straight? Is it going up? Is it going horizontal? Yes. And where would it be? Where would this approximately be?
Approximately.
Like where would it be in relation to this draft? Like, this is a rough copy. This has no number. Where would it be?
About the
Above, on, or below the x-axis?
above.
Above, because it's positive. Good job. All right. What? Okay, Rachel, I don't know what you're saying right now. You're very confusing. All right, so back to the lesson. It would be here. Okay, so now this should be a breeze then. Okay, so what would this produce in an AT graph? What would this line produce?
It would be a line just like going straight vertical down.
Like this?
No, like on the start from like the positive side.
Like this?
Oh no, like so it is a vertical line, but like so like
Okay, a vertical line is this. Are you talking about horizontal line? This is what a horizontal line looks like.
oh no, I said vertical.
I know, but how can it be but explain your thought process on how it will be vertical.
Oh well, like so it's meeting like the 0 point, right? So like wouldn't it be like a vertical line going down to meet the 0 point?
So like this.
Are you saying like a straight vertical line through the graph? Tony, draw a vertical line through the graph. Is that
Like this. Like this is the vertical line.
like?
So I think you're talking about. Are you talking about a horizontal line or a vertical line?
Vertical.
Vertical. Okay. So now explain where the vertical line would go.
Actually, I'm not so sure.
Okay, that's what I thought so too. Okay, so
Wow.
remember. What do you mean? Wow.
Just going wow.
No, that was just some very confusing language. I was like confused myself. Okay, so remember that lines have constant slope. That means the slope anywhere of this line is going to be the same. So if we do a vertical line like what you're saying, so you don't so do you know so when you said vertical line, where do you think the vertical line would be? What idea were you trying to communicate?
Oh wait, never mind. It's just that I don't know.
So are you talking about these type of lines? Like these type of lines?
Yeah.
So those are horizontal lines. Okay? So remember that this is simply, we find the slope of this, we get the graph of this. This has a negative slope, it's going down. So it's going to be here. This is a negative slope. This has a positive slope. So these are also really simple conversions. So to summarize, right? If we were to summarize like that, the slope is positive, the slope is negative, the slope is positive, and the slope is negative. And I realize that these look the same, so I'm going to draw an arrow. Oh, this is exactly why I should have drawn an arrow before this started. Okay, so above, below, below, above. All right, so that was just a summary on how curves turn into lines, which then turn into flat lines. Do you sort of maybe have a conceptual understanding of what's going on?
Yeah.
Yeah, okay. Let's see if you actually have a conceptual understanding by doing this question, which is like one of my favorite questions in physics. So this is going to be a DT graph, right? And you're going to convert it yourself to a VT and an AT by describing to me in the language I want you to use, like try to be specific as possible. Horizontal line, where is it? Above or below? Where is it from? Where is it to? That sort of thing. Okay, so this is what the graph looks like. All right. So you're probably okay, so 1, 2, 3, 4, 5. All right, let me break it into components for you. Curve, straight, curve, middle, straight, curve, straight, curve. Okay, this is like a horrible diagram, but let me just try and fix this. Okay. Like this, like this, this, like this, like this. All right. So these are curves. This is straight. This is a curve. This is a curve. This is straight, and this is a curve. All right. So let's convert it to a velocity time graph. Okay. So how would you convert this? This is this is an interactive part of the lesson. So this part we really need to focus in how to do this.
It also seems
All
like
right.
a bit of a challenge question, so
Yeah, it's a bit of a
looking at
challenge.
struggle.
This is basically like everything we talked about all in one, like literally all in one. But yeah. Okay, so how would we convert this to a velocity time graph? By analyzing each section. So let's analyze the first section. This is a curve. What would it produce on a velocity time graph?
Like a a a slanted line.
A slanted line that goes from. Okay, so you're gonna say what it produces, like what line, where is it from, where is it to, and describe the behavior of it, like a bit of the behavior. So it is a slanted line, and where would it be from, and where would it go to?
It would be from 0 to a a bit right.
What do you mean a bit right?
So like
It's up or down?
up.
Up. Okay, a bit right up. I mean no, a line that goes up. Okay, it goes up. That's the first section. You're right. Okay, so what about this section? A straight line. Straight
Is
line. What would happen?
so it would So if it's this straight line, it would be like a horizontal line.
Yeah. And where would it be?
It would start from the point where we left off, like we
Mhm. And where would it go to?
to so like a bit left from the middle point.
What do you mean a bit left? Like here? Like it goes
Like,
back in time?
No. So like it will start from that point, go right, but like yeah,
And it would stop. Right?
yeah.
Okay. Then what about this curve? What happens to this curve?
So that curve is getting flat.
So
It would go. It will start from that point, going a slant line going right. That's going downwards.
okay, they're all gonna go right. You don't have to keep saying they're going right. So it'll go downwards. So it's
Going
slanted
slant, yeah.
like this. And where would it stop?
It will stop on the. It will stop on the. It will stop on the 0 point
X-axis.
x-axis.
There's no zero, but this is a 0 point. This point is 0, 0. This
Okay.
point is some value of x and 0. So this is called the x-axis, okay?
Okay.
All right. What would happen to this part?
It would go on. It would go on to the negative side. So like from the point left
Okay,
off,
so what type of line would it form, first of all?
it will form. It will form a. It is a. It is flat. Wait, no, it's
What?
it's a steeper line. No, wait, no.
What are you trying to say right now?
I'm just trying to like say what kind of line it is.
So this line, okay, think of it as a reflection. This line reflects this line. So this line's going flat, so this line's going like this looks like it's going. Okay, it doesn't look like because it's a bad drawing, but it's supposed to look like this.
Okay.
So what line would it form on a velocity time graph?
So it will be a line.
What kind of line?
Like a straight line going
A straight line with a slanted line.
slanted, going down like from
Okay, and where would it stop?
up
Roughly, where would it stop?
roughly about at
A, B, C, where would it stop?
at point A.
Roughly, I would say that as well. Okay, and then later, can you justify why it would stop at around A?
Cause like so like the speed is like so it's like well like the speed is like decreasing. Wait, no, it's like
Okay, maybe you don't understand why. Okay, so let's just continue on. I'll explain why. What about this part? What would happen to this part? What line would it produce and where would it be?
it would it would be a
This
It would
is
be a
not a curve. This is a straight line. What would it be?
line. So start from that point. It will be a straight horizontal line.
A straight horizontal line.
Yeah.
Here?
Uh,
Here? Where would it be?
Oh, right.
Okay. Right? And how long would it roughly be? Compared to this? How long?
It would be
It would be the exact same, but we'll see why it's going to be the exact same. Okay? And then what's the final section going to be?
it would be a line, a slanted line that's going to go up and meet the x-axis.
Mm-hmm. All right, like this, right?
Yeah.
And where would it stop at?
And you stop at just there.
Yeah, stop at the x-axis. Be specific, okay?
Yeah.
All right. Now let's go over why this is what it is. You basically use the same logic, but faster, positive, fast, steep, steep and positive, like this. Constant and positive, like this. Positive and slow, so this. Negative but fast, so this. Negative but constant, so like this. And negative but slow, so back to 0. So when I'm asking you for the rough size about this, you should notice that this and this have the exact same area. So why do you think this shape and this shape have the exact same area?
Because on the first graph, like it's just like a reflect of like the first half of the lines.
All right, kind of, but how would the reflection create an equal area in both sections of trial and in both the journey in the journey of the object?
I don't know.
Don't know. Okay. So the final displacement of this object is 0. It comes back to where it originally goes. Zero, right? It technically hasn't moved at all, but there was there was but there was a formula that we can actually use to describe this. So do you remember the formula on your paper? It's displacement. Final displacement is top area minus bottom area. Do you remember this formula?
Yeah.
So top area minus bottom area, right? If the displacement is 0, that means the top area equals the bottom area, right? So if the top area equals the bottom area, the object does not move. So that is something that you should note. When the top area and the bottom area on the velocity time graph, the object does not have an apparent displacement. Okay?
Okay.
So we can see this on the displacement time graph where
Yes.
it ends at 0.
Yeah.
Final displacement is 0.
So with your little reflection thing, I think what you're trying to communicate is that the behavior of the first half should be opposite of the bottom half, but just in a different direction, something along the lines of that. So it's fine. All right. The challenge question. Now, this is pretty challenging because it's like all the parts at once. All right. So what would the acceleration time graph look like then? If you have the velocity time graph, what would the acceleration time graph look like?
So first it would would have a line, a horizontal line on the positive side, moving right.
There's no moving right. Just say where it is
Going
and
left.
say what shape it is.
A horizontal line.
Horizontal line, and would it be okay? Okay. For this, we're gonna simplify it a lot. Just say if they're all gonna be horizontal lines. Just say if it's above, on, or below the x-axis. Okay.
Okay.
All right.
Uh,
Okay. Go.
above the x-axis,
Mm-hmm.
and then mm, on the x-axis,
On. Okay. Good job. Okay. Continue.
and then it would go under the x-axis,
Okay. And then.
and then mm, and then back on the x-axis.
Back on the x-axis. Explain why it would go back on the x-axis.
Because on the second graph, like
Remember, we are analyzing this section. The slope of this, what would it be? Where would it be? On, above, or below?
it would be below again,
Okay. And
and then it would be on the x-axis,
then.
and then it would be above the x-axis.
Okay. So here's where I think you're confused, right? I made this mistake too on a test, so I'm gonna tell you right now. If I had a question and it was like, find the slope of, find the acceleration when it is at this time period, right? And it said 0, and people are tempted to say, well, at this exact time, the object is not moving, so it has no acceleration. So they would put 0 meters per second squared. Well, this is wrong because the object is not moving. Okay.
All right.
Okay.
I lost
Hmm.
audio.
Oh, you lost audio. Okay.
Talking for like a weird amount of time just now.
Wait, what?
It just happens sometimes. Sorry about that.
Keep going with
Okay. All right. I mean, the lesson is over in 3 minutes. So, but basically, if something is like, if I tell you to find the acceleration of at a certain time period, and the time period is at 0, right?
Yeah.
Is at 0, then you don't say that the acceleration is 0 because the object is not moving at that point. Like at that point, the object is quote unquote not moving. But in reality, what's happening is that your object is just turns direction because it was used to be positive, now it's negative, right?
Yeah.
So that's why we do it. And the object, it's not moving for a prolonged period of time, so it's not. So it does. So the acceleration is still there. It's just not. Rachel, how would you explain this? Like you have to think about the bigger picture, okay? Just because it's on the x-axis doesn't mean it's not moving or accelerating, okay? You still need to calculate the slope of the greater line to find the acceleration, because as we said, only in this moment of time is it not moving, but throughout its journey, it's actually like still moving. Like in real life, if you were going through this person's path, right? It would be like you walk and then you turn around. And in the time that you turn around, which is like really, really quick, that would be your at rest moment. So, therefore, my point is the acceleration at a line where it touches the x axis, where it touches 0, does not have 0. Okay?
Okay.
All right. So, basically, that was drafting entirely. So to quickly do a review in the last minute, dt to vt to at. So how do we get to dt to vt? What things do we use? This is a review.
Slope.
You have to answer. Slope. Okay. To get from vt to at, what do we use?
Also slope.
Yep, slope. So get to vt to at, what to vt to dt, what do we use?
The area.
Area. Okay. And that's it. That's all you have to know. And the other shit, I'm that was a slip up. The other things that you have to know.
Y'all heard
All
nothing.
right.
You heard nothing.
Okay, that was actually a slip up. That was actually my bad. But the other things you have to know, it's not a list, that's why. But the other things that you have to know is basically like this thing, the how steep the slope is, and how that affects other graphs, and you're basically good. So basically this table. And then next class we have one more physics lesson, which we're gonna cram in stuff like force, energy, work, efficiency. Wow, that's a lot of things. Weight. So yeah, good luck, and I'll hope to see you next time. Okay, yeah.